Hello, everyone. Shall we get started? Yeah, so it's the end of the day. I think everybody's tired, but I hope I'll keep you awake for the rest, until the end. I forgot to say the other day, apologies to Cedric Villani for the title, All the New. I didn't know what to call it. So yesterday we talked about the classical Schrödinger bridges coming from the ideas of Schrödinger in large deviations and most likely. So today we're going to shift to quantum. Here. So again, thanks to IPAM and the UCLA, and also thanks to my collaborators, especially Olga and Ralph. Olga is here today for a couple more days, and Ralph is going to be here most of the 3 months, and Michele Pavone and also Andrew Jordan for some comments and insights. So I'm going to do a little recap on classical bridges to set the tone. Then I'll talk a little bit about the first attempt to build some quantum bridges by Otto Bergmann. And then a parallel development in physics on certain ideas by Aharonov and some of his collaborators on creating what's called the two-state formalism, which very much echoes some of what Schrödinger probably wanted to do. So on that, we're going to build on certain types of Schrödinger bridges, which turn out to be very close to classical. And then we'll talk about, I don't know, this, okay. Then we'll talk about quantum channels in general, and again, some results and some conjectures. I hope I have time to give an interlude on a different view of non-commutative transport, basically closer to Cullen and mass, and then close with some discussion and directions. So again, starting slowly, B is a Brownian motion. This is classical setting. You have a diffusion, no drift. If there is drift, there's no big difference. So in that context, you have the probability law that gives you the probability of the random variable taking values in some window, given the beginning, and this is given by the Gaussian kernel. Now, when we talk about bridges, usually you pin the law at 2 points in time at 2 different spatial places. And then basically you're restricting, you have the law on paths, and then you throw out all the paths that don't meet the marginals. And now you have a new law, which is the law on this. This is a conditional probability. And in this context, you ask the question, what happens, what are the statistics of x of t in between, given the marginals. In this case, Bayes' law is going to give you some density at point t that will give you exactly what you want. So Schrödinger went a step further from that, and he said we have 2 empirical measures at the beginning and at the end, and they may not agree with the law. So basically, he wants to do a soft conditioning on these 2 marginals. And that's exactly what the Schrödinger bridges is. It's, and we explained before, because he was looking for the most likely. So the probability law, when you do this conditioning, is the one that minimizes the relative entropy to the prior, subject to the marginals. The story, whether in discrete space or continuous, is the same. You have this integration of measures, and the relative entropy breaks into 2 integrals. One of them is set to 0, which basically tells you that the pinned bridges have the same law as the prior, and then you optimize the other one. Now, I would like to make a parenthesis here to explain, because we're talking about optimal transport, that those 2 things are not very different. We discussed this last time from a certain angle, but this is another take at this. So if you remember, in optimal transport, you minimize a cost subject to some probability law that you specify the marginals, for example. This is the Kantorovich setting. And then often we look for a regularization, which is typically the entropy, or the entropy relative to the product measure, or the entropy, relative entropy to any prior. So there's absolutely no difference. You can take the cost functional and you can write like this, minus log e to the power cxy, and bring those two things together. And basically you have a Schrödinger problem with a different prior measure. So the Schrödinger problem encompasses the regularized transport problem. Okay, this is just to make a little bit the connection. Those of you who have seen it, you know it, but I think it's quite insightful to draw the connection, okay? So that's why we're focusing just only on that, and this, again, encompasses optimal transport. So this is, again, the picture of the disintegration of measure. So if you have the prior, law on paths, the Schrödinger bridge matches the two marginals, so it's a soft conditioning. And it is the coupling and the bridges. And this is a picture from a paper mapping the optimal route between two quantum states by Andrew Jordan and collaborators. And this thing here represents a quantum system weakly monitored over the duration, where you pre and post select a state. So basically this appeared a couple of years ago in Nature, and it's nothing but a pin bridge. And basically what they were doing in that paper and some subsequent work, trying to find the law for exactly these pinned quantum processes. And we are going to take a very similar route, trying to generalize slightly this concept of pre and post selection by allowing at the two ends to have marginal densities. But again, marginal density matrices with respect to fixed bases. And this is going to be the first part of the talk. Oops. Okay. Let me again remind you a little bit about how the Schrödinger problem is solved. For reasons we discussed last time, you end up with the structure of the solution having a certain particular form, and this was already discovered by Schrödinger. And then when you try you can look at the dual functional, there are different ways of approaching it, you end up with the following theorem that the density, this is again classical, factors as a product of two factors, phi and phi hat. The phi hat propagates forward with the Fokker-Planck equation. This is the Gaussian kernel. Again, apologies that the notation from slide to slide, there might be a slight discrepancy before I use G, but anyway, this is the Gaussian kernel. So in order to solve the problem, you have to find a way to factor the rho into a product of phi and phi hat. Yes, that's correct. Phi and phi hat at the two ends of the interval you're considering, 0 and 1, where the phi hats relate through the forward map. This is the Fokker-Planck, and the phi is through the adjoint. And you can do that very conveniently and think of how you do it by the synchrone iteration, whether discrete or continuous. So what you do is you take some choice for phi 0 hat. You can take this to be equal to rho 0. Propagate forward. For example, if the prior is a diffusion, is a Gaussian, you have a Gaussian kernel, you propagate forward with the Fokker-Planck. You compare it with rho 1, and if it's different, you find the scaling that makes this equality. That scaling, you propagate backwards with the adjoint, and then you repeat. And this, the cyclic, yes?
Sorry, maybe a stupid question if you covered it yesterday, but those scaling factors, phi 1 and phi 0, do they somehow relate to the Lagrange multipliers?
Yes, they are the Lagrange multipliers, yes, exactly. This is nothing more than the synchrone iteration. And as I explained the other time, the first person who proved, actually, Schrödinger said this is the solution. It has to have a solution because it makes physical sense, and that was his proof. And then Robert Fortet, 5 years later, he had a rather complicated argument to explain that actually this system converges under certain conditions. In fact, my collaborator, Michele Pavon, he spent quite a bit of time and he wrote a paper, I think it's on the archive, I forget where it has been published, with a title, something like A Magnificent Proof of Robert Fortet. He went through that paper very, very carefully and basically rewrote it, okay? So, and it's very, very interesting. It's completely different. The way we discussed and proved it last time using the Hilbert metric and the contraction of the Hilbert metric. So again, this is a retake on, this is again the schematic I showed the other time. You have the starting density and the ending density. You have to factor them into phi hats and phis that match. And then everywhere in between, the one-time marginals is the product of the phi and the phi hats. So this particular Gedanken experiment by Schrödinger and the solution that he came up with piqued his interest because it has a close resemblance to the Schrödinger equation, which is here. So you can think of the phi hat as the wave function and the phi as the adjoint. Of course, those two are vastly different and they're real. Those are, of course, complex conjugate of one another, but the probability one-time marginals are the product nevertheless. So for the quantum setting, the rho could be a probability density or more generally a density matrix, and the question is how exactly what ways you can generalize this to basically link beginning and end density matrices. So the first attempt to do a bridge at the level of quantum states, and this is more like a pin bridges rather than Schrödinger bridges, was by Otto Bergmann in '88, and he prefaces the paper by saying this is an unauthorized, in quotes, extrapolation of ideas of Schrödinger, etc., into the quantum mechanical domain. So, for example, consider initial and final states and think of them as eigenstates of some observable, initial and final, I for initial and F for final. And then you can just write an interpolating law, which basically, how does it go? Right. It takes the initial state into the final. He wrote down this expression. You have here some sort of a rotation operator, and here is the interpolating time, how t varies distances from t0 and t1. And if you spell this out, it becomes cosine of pi. Oh, this is t, sorry. This is t. Oh, this is tau, sorry. That's tau, right. So this thing here I call tau, and it goes from 0 to 1. So it's cosine pi by 2 tau, sine pi by 2 tau. So this is an interpolation, okay?
There's an imaginary I missing. There's an imaginary I missing.
There's what?
An imaginary I missing.
The imaginary I missing. Yes, there's an imaginary I missing there. I have a lot of eyes there, so sorry. Yes. So, yes, absolutely, yeah, thank you, sorry. Yeah, and it's also here, yeah.
Are you assuming them to be orthogonal?
Sorry?
Are you assuming I and F to be orthogonal?
Yes, yeah. Actually, not necessarily. I don't think this is, I think this applies to, so the bridge interpolates between those two. I don't think this, just 1 second, yes, yeah, so the I is missing. No, they don't need to be orthogonal. It's algebraic expression for interpolating, yeah. So basically, this construction, restores some resemblance to the Brownian bridge, which we just saw earlier. That you have a portion that tells you it's some sort of a product. So if you now measure some state k at some point t in time for some evolution, okay, you have a probability law that says the probability of going from f to k and from k to I squared, and you have expressions like that, and the bridge of Bergman does that. However, if you look at it carefully, there are some drawbacks that I evolves into a mixed state and back to f, which implies some entropy decrease at some point. And then the other thing, which is a bit more serious, is that the normalization depends on the time when some projective measurement takes place in the middle. So it's not like in the Brownian bridge. And discusses non-selective measurements at t and writes the law in some sort of a product form. So this was sort of a first attempt to doing something like that.
So what is exactly, like, do we have some expression for ZT, the normalization?
Sorry?
Do we have some expression for normalization?
Yeah, it's a bit, it's basically, I haven't written it down. Yeah, but it just depends on t. Now, Bergman writes a few things. Schrödinger's main interest was statistical mechanics and interpretation of quantum mechanics. So that himself was inspired by an old and almost unknown paper by Schrödinger. No attempt was made to draw any conclusions about its impact, if any, on the theory of measurements. It was written primarily as a historical study and an exercise. Then a referee informed the author, Bergman, of some work by Aharonov, Bergman, and that's not the same Bergman. The first one is, what was his name? Otto. And the other one is Paul, or Peter. Peter, I think it's Peter. Right. And Belifante. Contribution to the same problem, written without Schrödinger's inspiration. So Aharonov and his collaborators were very much interested, and so was another fellow who was even earlier, Watanabe. There was a circle of ideas that led to what's called the two-state formalism in quantum mechanics. The basic question was, again, very similar to what was bothering Schrödinger, that you have some sort of directionality built in, that you make a measurement and it goes forward and not backwards. You wanted to restore the concept of bidirectionality. And so were this latter group of authors, as well as Watanabe, who was probably the first one to look at this symmetric formalism, where you have a pre- and post-selected quantum systems, and was seeking to try to find a symmetric description of quantum mechanics evolving backwards and forwards between psi 0 and psi 1. So again, Aharonov, Bergman, and Leibovich came up with very similar ideas a few years later, and they wanted to deal with the asymmetry in time that is not due to the principles of quantum, but only in the intrusion to the microscopic world by virtue of making measurements. So the whole idea of this two-state pre- and post-selection is that you can run an experiment, you can prepare your states, and then propagate forwards, make whatever experiments you get, then you go to another end, and you make another projective measurement, and you only keep what happened when the outcome of the projective measurement is the psi 1. Oops, sorry. the psi1. So for example, you can pre-select, do the measurement, projective or weak or anything else, and then you post-select. So given a sequence of measurements of arbitrary observables, a time-symmetric expression is obtained for the probabilities of measurement outcomes. So you can write, and this is more or less classical, that the probability of measuring x given psi0 and psi1, this is classical probabilities because right now after you have pre and post selection you have an ordinary probability space. And this is simply the probability of going from psi0 to x and x to psi1. You may or may not have evolutions in between. So if you don't, and this is exactly the setting of Haranov-Bergman, so you have unitary evolutions or no evolutions at all, then you have this expression. This is time-symmetric. If this time-symmetric is taken as the fundamental algorithm of quantum mechanics, now to some degree they restore time symmetry, but then on the other hand, they were worried about what assumptions are required to retrieve the standard predictive probability expression in quantum mechanics. So there were lots of sort of questions that popped up. So we'll see a little bit. So now Belifante extended the work of Haranov and others to non-ideal measurement processes. In this setting, he thought that the presence of intermeasurement process breaks down the time symmetry. But we're going to see that basically this is kind of an artifact. In fact, you do have a rather symmetric picture in terms of the time. So here is sort of the setting. You have a pre-selection starts at 0. Then you measure at some point in the middle, and then you end at 1, and you have post-selection. You may or may not have some stochastic evolution or a Krauss map connecting the various pieces of this. You're going to see another picture. It will make it more clear in the next. So this is reading, so the probability, again, I kind of rewrite it here. The probability of measuring x given pre and post selection is given by this expression and reads forwards and backwards in somewhat of a symmetric way. But the moment you introduce, let's say, a Krauss map with coefficients L dagger, I always put for the Krauss map a dagger here to echo the framework in probability theory where the forward map is the adjoint of the semigroup. Okay. Then the two expressions are a little bit different because one goes forward in time, the other one goes backward in time. If you have L here, you have an L dagger on the other side. So next we're going to deal with this in earnest, and this is work of Olga's, and she can answer questions tomorrow or later. You can discuss more with her. So the whole idea is we fix bases at the beginning and at the end, and we have an assistant who sits in the middle and prepares the ensembles, reports the pre and post-selected marginals, and the bridge problem is to find the most likely outcome. So here is sort of the schematic. Again, I apologize, some of the notation is a little bit mixed, but I'll explain it so that it's not. So we make, we fix the bases at the beginning. There's no measurement in the middle here. There's just a Krauss map. So we have a pre and post selected with respect to some fixed bases. So the posterior is different from the prior. Rho 0 is the prior density metrics at the start. And then if we have a prior density matrix of the star propagating with a Krauss map, we are going to get a posterior density matrix at the end. And let's suppose that our assistant, who's preparing and post-selecting, artificially, without telling us, throws out some of the experimental results and gives us the rho 0 tilde and the rho 1 tilde. So these are the recorded data, and we want to find out some sort of a concept of what happened in between, how we transitioned. Here we do not have a measurement in the middle. Pretty soon we're going to do a measurement as well, so that we do the statistics of the measurement. So then what you seek now, we have the rho 0 tilde. So we want to find a correction of the Krauss map that maps the alpha tildes, because these are what they're reported to us by the assistant, to the beta tildes over here, that these are also reported to us. And this set of data are not consistent with the Krauss map. That's a density matrix. If we stick it in here, we don't get this one. So we just want to correct it. So again, the same frame of the Schrödinger paradigm and the synchrony iteration applies. So we have the prior, and this is prior, and those are consistent. We're given this, and we're given that, and we want to correct. So the thing is that now we have because the bases are fixed, we have, as I just mentioned, a classical scenario. So we can...
Can I ask a question for your picture before, which confuses me all the time? The arrows, after. The arrows down, they are completely random, or what do I know about the arrows down?
So the arrows down is signifies how do we... this is a prior, and this is a prior law, so to speak, right? This transition probability. Now, the assistant who prepares the experiment for us reports this one and reports this one.
So do we have some functional relation about, is the system linear?
No,
or
it's just, no, there's no map here. It's just it's an empirical. This is an empirical density, and this is an empirical density. And in this context, we can talk about large deviations because we're still in a somewhat classical setting. So the transition probability from psi 0i, and this is an element of the basis, to psi 1j, an element of the basis, is given by this, this expression. So this is sort of the prior coupling from I to j, which is the starting probability and the transition probability. Then we go, just as we did before, we look for an optimal coupling which minimizes the relative entropy subject to the new marginals. The ones that are empirical, and they're reported to us by our assistant. So the setting of the synchrony iteration applies, and we find that the posterior is again a correction of the prior coupling with, so this alpha I tilde and alpha I are reported, this we know, and we find two coefficients. These are the Lagrange multipliers, the scalings that change this non-commutative, so to speak, measure, transition probability, transition kernel. And we now have the tilde, which is the updated one. And we can write it and we can factor it in a very specific form in a way that is reminding us the structure that we saw in the Schrödinger system, that there is a matrix phi with the Lagrange multipliers AI and Bj, phi 1, And those can be conveniently sandwiching the Krauss coefficients at one end of the channel and again at the other end of the channel. And that is the form of the updated Krauss map. So this is basically a change of measure. This structure we're going to see also later, okay, in more general Krauss maps. So again, the Schrödinger system, I don't want to belabor the point, it's exactly what we've seen before. So you start from a phi 0 hat, you propagate with the prior Krauss map, you get phi 1, you go down by inverting the phi 1 on both sides, and you come across and you go up. Now, the thing that helps us show that everything works in this case is that the phi's and the r tildes at the two ends of this diagram can be diagonalized with respect to the same basis at the two ends. And that makes the problem effectively classical, and the synchrone iteration converges, and therefore you have existence of the scalings. So there's nothing that is terribly surprising. Now, let's talk a little bit about time reversal so that we see how the picture can be. I didn't talk about that the previous lecture, so this is somewhat new. So if you have a classical Markov kernel, let's say here's the stochastic metric. So we're looking at a Markov chain. So this is a vector, a probability vector. We multiply with the raw stochastic matrix, and we get another probability vector. This is a raw stochastic matrix if the sum of the rows of the matrix give you a 1. Right? So that's the condition. Now, if you have that, and if the rows are they don't have 0 entries, we can reverse time, and because we can define a joint density at the two ends of the experiment of the Markov chain. We have some Markov transition, right? You have probability that you start here and transition. Now you can have a joint. So because of that, we can reverse the time arrow, and then we can write this map, which scales with the diagonal, with the row 1s on the diagonal inverse. Then we have the pi, then the diagonal of row, and you can see that this maps the row 1 back into row 0, right? This thing here basically makes the product between this and that the identity, then you use that, and then you just scale again. And it's easy to see that the adjoint of it takes 1 into 1. Again, the 1, if it comes from the right here, creates a row 0, which becomes row 1, and then this brings it back to 1. So the time reversal, R here denotes time reversal arrow, so you just view, again, the experiment, you play the movie backwards. Then if you play the movie backwards, you're going to see exactly the same type of transitions or rates of flows between states of a Markov chain if you use this pi reverse as your raw stochastic matrix, which is this. The one catch is, but it's also important here, is that this depends on the states that you are at. Now, there is nothing special about classical, about this trick, and it's quite natural. You can do it exactly the same for quantum channels. So if you have a Krauss operator here, right, this is trace preserving. So the forward, so now these are density matrices, row 0 goes to row 1, and the identity matrix goes to the identity matrix with the adjoint map. Then you can see that if you reverse time, provided the inverses that are given here exist, takes row 1, sandwiches with the square root of its inverse. So you get the identity matrix. The adjoint of the Krauss maps gives you the identity, and then you multiply with that. And then you have basically a Krauss map in reverse. So this is the time reversal for Krauss maps.
By the way, this appeared in the work of Evros and Lanz in 72.
The work of?
This appeared in the work of Evros and Lanz in 72.
This has, it's standard, it's quite, right.
Yeah, they just used it for learning algebras.
Yes,
many years ago.
Many years ago, I'm sure.
I mean, it's just, there was...
I don't know where this thing was first done. Yes, go ahead.
For the Markovian universal, you need ergodicity in one class only.
No. I mean, here the only thing you need is that the inverses exist. That's all. Okay? And it's one step, so there's no issue of ergodicity. Now, sometimes for what we're going to do later, there is a notion of positivity or strong positivity that comes in, which would be important. So there are some subtleties, but not here. This is just straightforward. Okay, so then you can ask the question. You can say, okay, fine. You have a way with the synchrone iteration. You have some surprising data at the two ends of the quantum channel that were reported to you, and your prior Krauss map has been replaced now with an updated Krauss map. How does this whole thing work under time reversal, right? So we have the experiment we had before. This is the Krauss map. The assistant reports to us the starting and the ending densities. And we allow the synchrone iteration to produce the factors and everything, and then we have the updated Krauss map. So it turns out that if we do a time reversal, so instead of looking at the data that were given to us, row 0 and row 1 in that order, we look at it in the reverse order, then we're going to have the reversed out Krauss map for the nominal data, and this is denoted here by the coefficients by m. So suppose now we just look at the data backwards, and we do exactly a for-test synchrone iteration, and we update the coefficients. Then the coefficients relate to the updated in one time direction exactly via time reversal. So the diagram commutes. So this is kind of the symmetry that one should seek in this setting. That, and we're going to look at it also now when we start having experiments here in the middle. So now we move to a little bit more demanding situation. It's not technically more demanding, but you would like statistics or path probabilities. In the classical setting, you have sort of the marginals that you match, and you ask the question, what is the most likely value, or what is the distribution of the marginals in the middle? So in exactly the same way, we can think of the assistant reporting to us the initial and the final density of an experiment, and measures, perhaps non-selectively, some observable somewhere in the middle, some point t between 0 and 1. Then the total Krauss map that maps a pre-selected state x0 I to y1j goes through a first Krauss map, could be a unitary evolution here, and then goes through a non-selective measurement in the middle. These pi here are projection operators in the eigendirections of the observable z hat, and then followed by another Krauss map. And reports only the initial and the final, which do not map the expected. And again, the Schrödinger dictum, now we're more in the line of what Schrödinger would have been interested in knowing, what is the path in between. Because this probability law gives us some information about what could have happened in the middle. And we can go through, again, crank exactly this, the frame of the cyclic composition of maps. And we can write, first of all, the probability of observing the eigenstate Z at some point tau with pre and post selection. It can be computed. This expression, the top weighs in the beginning and the end. And then I think here probably I have a dagger missing or in one of them. No, I think it's okay. Probably, it's okay, because this is the other way around, yes. So these are the pin bridges. So the statistics in the middle given the pin bridges. Then we seek the most likely coupling, because these are the data we're given, and this can be determined by Singhorn, so we can happily declare that the posterior is this. And this gives us also updates in the Krauss maps from beginning to Z and from Z to the end. So we can write now the most likely distribution of outcomes in the middle, some point tau in interval 0, 1, like we did in the previous page. And it is not too difficult to factor it again as a product of factors, phi hat. And one of them, the hats, again, moving forwards, and the phi's moving backwards. And also into, right, so these are unnormalized probabilities. Their products is a probability density. So these are unnormalized you can think of phi hat as a probability density because it propagates with something that looks like the Fokker-Planck equation, but it's unnormalized. The product of the two gives us the answer, and it's exactly in the style of Schrödinger. And now we can also answer the question, what's the most likely state at tau? So the most likely state at tau is exactly this probability of observing Z times the projector, and you can write it as a product of phi's and phi hats, but in a symmetric way. Here, because they're all expressed with respect to the same basis, everything commutes. At every point in time, at the beginning, the middle, and everything commutes, and the solution also is identical under time reversal. I don't want to bore you with this, okay? So you can do the same thing with weakening the measurements, generalized measurements of various sorts. So the assistant can weaken the measurement. You just have a different Krauss map in the middle. You can have projective measurements, etc. And so this kind of extend in different ways the program of Aharonov, Albert, and Weidman. And this is a simple example where there is an amplitude damping experiment. This is an academic example. So at one point in time, the assistant prepares it is a two-state system and prepares it in a suitable density matrix, probability of up being this, probability down being that. So we have this in the paper. Now, what these pictures denote is the probability of measuring Z and the Z is 0 or 1 in the direction of Z. So it's prepared for instance, you prepare in the X state is up or down with some probability, and you measure, let's say, the Z at some time t. Now, the most likely, now this is nothing evolves here. This is a one-time measurement. So if you specify the t and you make a one-time measurement, the probability that you're going to get z prime equal to 1 or z prime equal to 0 is given by the dashed line, and that's the prior. And the posterior is here, because the assistant reported to us marginals. So it's just a correction. Now, I want to repeat that this is not a dynamical sort of evolution. This is stitching together measurements that you might be able to be doing at any point in time. Okay? Okay, so the summary of this is that with specified basis and intervening measurements, we have at one end of the channel, we have an ordinary probability space. It's just the fixed basis of the eigenfunctions, some observable, and so is at the other time. And the Schrödinger bridges become manifestly classical in this setting. It has a large deviations interpretation, and you can define Haranov and his colleagues defined something called the weak value. Here you can define the most likely weak value and the update of the Krauss maps. So this is a first part of this talk. Now we go to a slightly more complicated setting, where this is a purely non-commutative quantum Schrödinger bridges setting. And there is some material in Wikipedia page. Actually, I put some of that. This is mostly joint work with Michele Pavone. And I'll be talking mostly about that. One result that we had in there, we learned actually from Idle Martin after we submitted the paper that was also in Leonid Gurvich's paper, which is actually a very interesting paper, Classical Complexity and Quantum Entanglement. So the setting now is the following. You have E dagger denotes a prior Krauss map. F denotes the posterior. So you're given the Krauss map. It could be a one-step Krauss map or many steps. It really doesn't matter. So if this looks complicated, just think of it as one step. There is absolutely no difference. This is like propagating, you have the concept of the path, so to speak. And the prior is inconsistent with final and initial densities. Here I didn't call them R tilde. So these are the ones reported. And those are not measured with respect to any specific basis. So they are arbitrary rho 0 and rho t. And then what we want is to determine an updated Krauss map that matches the marginals. And from here on, most of the things I'm going to tell you are mostly questions and very few answers, okay? So for example, you would like to compute, these are transition probabilities, right? This Krauss maps. And you would like to update the condition probability in some way so that the new one is close to the prior in some natural sense. Now, I don't know what the natural sense is. And this is actually, I'm hoping the next 3 months, we join forces and understand. I think some of you have great ideas. And so all right. Now, we're going to replicate this idea that we saw in the previous development, and also what is suggested by the Schrödinger solution in the classical case, that the corrections be local transformations at the beginning and at the end of the channel. In other words, these are Krauss maps with only one coefficient. There's a phi and a phi at the next step that you divide on both sides, and then you multiply on both sides. So now one result we have, which it's not trivial, but this is also in Gurvich. Our proof is extremely simple. It's absolutely trivial, but the result itself, the moment you look at it, is not. When the two marginals are the identities, given any Krauss maps, now there is a slight condition here that it has to be positivity improving. Positivity improving means that it maps the positive cone into the interior. If you remember from the previous lecture, the Hilbert metric, when you have a positive cone and you have a linear map, when you have this property that maps into the interior, is strictly contractive in the Hilbert metric. So when you have this condition, then you are guaranteed to have scalings, phi 0 and phi t, such that here you don't need to take the square root. You can take any factorization. So you take the square root here inverse, the square root here inverse dagger. If it is the Hermitian square root, then the self-adjoint square root, then you don't need the dagger. And then you multiply with the other ones at the other end. And this becomes a doubly stochastic Krauss map. In other words, maps I to I, and the dagger is also I to I. And if you have a sequence from 0 to t, the sequence of factors update all the e's in between in exactly the same way. So in other words, it's almost like a non-commutative change of measure, point-wise, in the densities, that allows you to have if you like, an updated flow that matches the marginals. And the proof is two lines. You just have the Krauss map going forward. You choose any density metrics, or normalized or unnormalized, it doesn't matter. You propagate, you look how close it is to the identity, and if it's not equal to the identity, you invert it. You invert it, and then you propagate the inverse. You look how close this is to the identity. If it is not, you invert it, and you go on. And the composition is strictly contractive in the Hilbert metric. That's the proof. It's strictly contractive because the inversion here is an isometry in the Hilbert metric. Okay? And the forward and the backward here mappings are strictly contractive. This is it. Okay? So now, let's go to the more general case. It's just a simple observation, if you like. It's not a theorem, that if you're given the E dagger and you're given a rho and rho t, and let's say that E dagger doesn't take rho 0 to rho t, so you need to update. If you can find a solution to the Schrödinger system, now that's the Schrödinger system, you map, oh, I have it wrong here. What do I have? Oh, yeah, that's correct, that's correct. The dagger maps the phi 0 hat to the phi t hat. That's the forward, and this is the backward. So the phi t goes to phi 0. I should have put this one second line. And then at the start and at the end, the rho is the product of phi 0 and phi 0 hat. So if you have a solution to this system of equations, that's nothing but the Schrödinger system in the non-commutative setting, for any factorization of those, then this map, where you first divide by the square roots and then multiply by the square roots, is a quantum bridge that maps the starting row to the terminal row and I to I. So the whole ball game is to show that the system of equations has a solution. We don't have a proof in this generality. We only have when the marginals are the identity and when the marginals are rank 1. What is going wrong with the previous proof is this, that when you go from phi to phi hat or from phi hat to phi, namely, you go here, you have phi hat, and you want to go to phi. Here, what you need is the product of phi hat equal to the marginal. The marginal is the identity. If it is not the identity, the way you solve this is more complicated. Okay? So here is how you solve it. So you need, for example, at one end, right? At one end, I give you phi hat t, and now you want to have the phi t half, so that this equation holds. The solution is pretty messy. The phi t is this. Okay? At the other end of the channel, it looks easier, but it's not any better. So if I give you phi 0 hat, right? Sorry, phi 0 half, right? You need to compute phi 0 hat. So the phi 0 hat is this one. It looks much simpler than this, but trust me, it's more or less the same trouble. Those maps are not an isometry in the Hilbert metric. Perhaps there is a twist of the Hilbert metric in some higher dimensional space, and I would like to hear any ideas. Because, and let me emphasize this, I've spent a lot of time with numerical simulations, randomly picking matrices and randomly picking Krauss maps up to dimension 20 by 20, I think, and it converges. The synchrone iteration, this iteration here, of going from phi 0 hat to phi t, computing the square root, coming back and so forth, converges. But we don't have a proof why.
Have you tried recovery maps?
Sorry?
Have you tried recovery maps?
The,
Recovery maps.
no. You have to tell me more about it.
Related to, I mean, it's sort of related to what you're doing. But
Okay.
It's very well used. So.
I'll be happy to hear more. We tried several things, but it is the structure is quite interesting. You know, it surprises you at every turn, and the thing works. And I don't, you know, it's just. I'll be delighted if in those 3 months we can get this.
I'm not guaranteeing that this procedure works, but maybe there is a modification, right?
Absolutely, a modification, anything.
Because they had a
Anything.
similar problem with recovery.
Right, that would be great, yeah. So this is just a simple example. You know, if you have a Krauss map, and this is total trace preserving, it's done in such a way so that you can compute it in closed form. This is the starting density, this is the ending density. The fact that this is diagonal is immaterial, because you can put unitary factors and make it any way you want. Then the solution of the Schrödinger system gives you this, and this is the posterior. And I have code, and I'll be happy to share it. You can just press carriage return, and you get a random Krauss map with whatever size coefficients you have. The only catch is that you have to have enough coefficients so that it is positivity improving. So as long as positivity improving, everything works. A question?
Yeah, so your problem, if I may just simplify it, is you just have a set of cross operators, and then you want to like pre and post multiply simultaneously by invertible matrices to be able to obtain something that maps like.
Exactly.
So we solved this. We solved this.
I'll be happy to hear.
Okay, I'll tell you later then.
Okay. I'll be happy to hear this. So this we had it, you know, for rank 1 matrices at the 2 ends, it works, and it can easy to show. And we had it basically, we had it in this paper with Michele in 2015 or something as a conjecture. So we were not able to show it at the time. Yeah. So I have another 15 minutes. So I'm doing well with time this time. So I would like to skim through an epilogue on non-commutative transports and then return with a recap and some discussions. So this is a style of non-commutative transform which is more in the style of Cullen and Mass. In fact, there were 3 papers Karlen Maass, Mittner, Zweig, and Milke, and a paper by ours, all in 2016, within a couple of weeks from one another on the archive. And then later on, there was one with Wilfrid on very similar set of ideas of how to do a dynamic formulation of optimal transport. The Kantorovich formulation, this was also at the time we were thinking about this, but we didn't quite think of a natural choice of H. And of course, we have seen a lot on that. It's a beautiful development by Augusto, and he talked to us, and there are many people working in the audience, so I don't have many references here. I just put one. The connection between the two is still a mystery, at least to me, maybe not to some of you. So the whole idea was, for those of you that have not seen this dynamic formulation, the whole idea is you like to replicate the classical optimal transport where we have a density and velocity square. So this is kinetic energy, and you need a continuity equation so that you match the given marginals. And you like to minimize the kinetic energy subject to those constraints. I should have put a min here. So how do you do calculus for matricial objects? For ordinary functions, if you have a function to be like an operator, the derivative is an operator, the commutator takes the derivative of the other operator. So the natural thing to do when you say partial of x with respect to L, when both of them are matrices, is a commutator. And if you stack many commutators one on top of the other, this is the analog of the gradient. And of course, the moment you have gradient, you can have a divergence because you have this inner product, how do we call it, Schmidt? How do we call this? Hilbert-Schmidt. And of course, you have, trivially certain identities. The gradient, the adjoint of the gradient is the divergence, and so on. And then you look at the Schrödinger and Lindblad equations. For simplicity, you can think of the Krauss operators, coefficients to be symmetric. And then this is the Lindblad equation. This is the Schrödinger part. And this is the Lindblad part, which is basically Laplacian in the previous notations, the gradient times the adjoint. So then the next thing is you try to think of how you can write this as a continuity equation. We need to have some sort of multiplication of the rho with a velocity field, and then we need the divergence of that. And then we need to write, there's another thing, we need to write the gradient of rho as some rho times the gradient of the logarithm of rho, which is going to give you some sort of a vector field. So the way to do this is, first of all, you need to decide how you're going to multiply matrices and get matrices of the right type. So for instance, here you need, V is going to be like a vector field, so you're going to be skew Hermitian matrices stacked together. And rho will be a Hermitian matrix, and then you have divergence of this and so on. So the question is, what is that? Suppose V was a matrix. Let's say suppose V is Hermitian and rho is Hermitian. How do you multiply two Hermitian matrices to get another Hermitian matrices? There are several ways. One is you multiply on both sides and take the average. The other is you multiply a little bit on the left, a little bit on the right, and you integrate, or you multiply with half of either side. Okay? So all of those three things and many more are legitimate, and you can do different geometries and different things with that. We worked out this one and this one. This is one that gives you quite interesting result in terms of gradient flows, but that also gives you other things. So then you say, okay, fine, I have my rho, and I want to multiply times v squared. So a natural way would be to multiply v with rho using any of those tricks. V is going to be a sequence of matrices stacked up, and then you multiply with the adjoint here. So this is like a column vector of matrices, and this is a row vector of matrices, and you take the trace. This red thing has to do with the multiplication. Okay? The trace has to do with the spatial integral, so to speak, and the dt is the integral from beginning to end in terms of time. And you can write in a similar manner, this is the momentum, because you multiply rho times v, and you take the divergence, and this is the continuity equation. So you can declare this to be the Wasserstein square distance between rho 0 and rho 1. You can develop duality theory. It turns out that this is geodesic space. The distance, so all the things that we expect go through. And interestingly, if you take the von Neumann entropy, and you take the derivative of that, and you played some tricks with some integration here, you can write it in this form, which tells you that the greatest ascent direction is you take the velocity field with the gradient with respect to the coefficients L of the logarithm. So that seems natural. And this was in the Carl and Maas paper. We did it independently and uploaded 2 weeks later. But the Carl and Maas paper is actually beautiful, and we relied very much on insights of Eric Carlin of papers earlier. So anyway, this simply explains that trick. This is called the miracle identity, that the gradient of that can be written as the product of rho times the gradient of log rho. Okay. Again, when you see the integral here, rho to the power s, rho to the power 1 minus s ds, that's just simply non-commutative multiplication. So this basically echoes Jordan Kindler Otto's famous result. And with that, I'm getting close to the end. So a little recap in terms of bullets. So quantum Schrödinger bridges, very much like in the classical setting, the idea is to interpolate arbitrary marginals. Restore consistency with data. The two-state formalism with pre- and post-selection. Time symmetry can be restored. Synchron applies. It's mostly classical. The general quantum channels, I'm looking forward to listening for new results that I don't know of, but I think the convergence of the non-commutative synchron we're not able to complete. And the questions that also remain is there a natural distance between quantum channels? Is there any connection with non-commutative optimal transport? Is this local transformation some form of non-commutative change of measure, and is there any large deviations interpretation? So this is all I had to say. Thank you very much.